matching in any undirected graph. Undirected, unweighted graph, sorry. Direction doesn't matter actually, so it is unweighted. So from our known vision, what is known that for any unweighted graph, the way we find a matching is by through some augmenting path. So there is a theorem which is called Bart's theorem, which we have already proven in our earlier classes, which says that a matching is maximum if and only if it doesn't have any augmenting path. Okay, so the same algorithm, so the theorem, it is not only true for a bipartite graph, it is also true for any non-bipartite graph, or in sense any general graph. So now since the size of the matching, if mod v is the number, so mod v is the number of vertices in the graph, so the maximum size of the matching could be mod v by 2. Okay, that we know. And what, so basically our strategy, what is our strategy? For a given graph, we basically find the augmenting paths. If I find an augmenting path, what we do, we will change the status of saturated edges to unsaturated edge, and unsaturated edge to saturated edge, and that's why for every augmentation, with every augmentation, size of the matching gets increased by 1. Okay, and since there are v vertices in the graph, at most mod v by 2 augmentations are possible. Now, as far as any bipartite graph is concerned, this won't create any problem. Okay, but for a non-bipartite graph, there are some issues, and we try to identify what are the issues and how that issues can be solved. So, say for example, the bipartite graph case. Okay, so basically, what we are trying to say is that how Bart's theorem is applicable to a bipartite graph, and why using Bart's theorem, why it is easy to find augmenting paths in any bipartite graph. So in bipartite graph, when we search for any augmenting path, it is basically efficient. And why that is so? The reason is, so to find the reason, better we draw a bipartite. Not we need to draw. So basically, what happened? Here, every vertex. So when I'm saying explore from each vertex at most one, so what we do in bipartite graph, if you recall in our matching algorithm, so bipartite graph has two partites. Now we can start from any one partite, and we choose any unsaturated vertex from unsaturated vertex, and from there we start a search. So what we do, suppose we take the partite, so there are two partite x and y. We start from partite x. Let's draw a figure, then we can easily visualize things. Okay, suppose this is my one partite, and this is my second partite. Now, what happened? Suppose this is an unsaturated vertex. From here, I start my search through some unsaturated edge. When I come back to the partite, I use some saturated edge here. Okay. Then again, from here, when I want to go, I go by an unsaturated edge. Again, when I come back, we come back to the saturated edge. So the point is, Now suppose I start from here, I come back to my original partite through a saturated edge always. And why? It is for bipartite graph. And when I go and when I reveal some augmenting path, I know that if I start from partite X and I discover an augmenting path, that vertex must be in partite Y. Okay, so see in this case there is an augmenting path. So what we do generally? So we revert the status of the edges. So what we do? It doesn't matter. Okay. So that is something written here. Okay, an M alternating path from U, which is an unsaturated vertex, can reach a vertex X in the same partite only along a saturated edge. And why that is always true for a bipartite graph? The reason is because bipartite graph don't have any odd cycle. Even if it has a cycle, it always has an even cycle. So it says that if I start from any vertex U, say U, I will reach to any vertex X in the same partite through some saturated edge only in alternating path, using alternating path. Okay. And this is true only because the graph doesn't have any odd cycle. So basically, suppose this is a bipartite, not suppose it is a bipartite graph, and suppose it has an even cycle. Okay. Now it is an unsaturated vertex. From there I go to V. It is a saturated edge. I go by VA. Now I can reach X like this, or I can reach X like this. So both are valid augmenting path. UVAX, that is a valid augmenting path. UVABCX, that is also a valid augmenting path. And this, so basically the search direction doesn't matter. So what I am trying to say here is, if I start from an unsaturated vertex U, we can reach any unsaturated vertex X to an odd length path. ये भी एक odd length path है, ये भी एक odd length path है. So as a result, the direction of search of search for an unsaturated vertex X does not matter. Does not matter. Okay. So X को मैं ऐसे भी ढूंढ सकता हूँ, ऐसे भी ढूंढ सकता हूँ. In any case, I will get an augmenting path. But what is the problem with non-bipartite graph? Let's see the case with a figure. Okay. So this is an odd cycle. Now you start from U, you go to V, there is a saturated edge. Now, if you go to A to X, you see that you reach X through an unsaturated edge, AX. Okay, and you find there is no augmenting path here. If you go by this, UV, VA, AX, you couldn't find any augmenting path. But if you take this path, UV, VA, AB, BC, CD, DX, and then XY, then you find an augmenting path. What I'm trying to say is, X can be reached from U through different paths of different lengths. So I should say from U you can reach X through paths of length of different parity. Okay. So agar main UVAX, if I reach X in this path, I will miss out the augmenting path. However, if my algorithm go like this, I can discover an augmenting path and I can augment. So a search for shortest M augmenting path from U reaches X via the unsaturated edge AX. Suppose हम लोग BFS use कर रहे हैं. Suppose we are going for BFS. So a search for shortest M augmenting path from U reaches X via unsaturated edge AX. If we do not also consider a longer path reaching X via a saturated edge like UV, AB, CD, X, then we miss the augmenting path, this UVA, BC, DXY. Okay, so that is the problem. So search direction matters here. Search direction always matters. Okay. So यहाँ पे जैसे सर्च डायरेक्शन मैटर नहीं कर रहा है. In any way we reach X through so UVAX, that is also so we can draw another figure also like this in a similar. Say for example, now UAXY, this is an augmenting path, and या यहाँ इसके लिए कोई प्रॉब्लम नहीं है. ये तो हर एक ओनली यही मारेगा. यू के बाद AX ही सर्च करेगा. सो देयर इज नो इश्यूज. जब यहाँ ऐसे बाइफर्क पड़ा नहीं, इट्स नॉट ए गुड एग्जांपल. सॉरी, इस केस में कोई प्रॉब्लम नहीं होगा. इस केस में प्रॉब्लम होगा जहाँ पे इट इज देयर आर टू अनसैचुरेटेड एजेस. In that case, for bipartite, there won't be any problem because you can reach X through paths of equal parity. Maybe length different होगा. इसके लिए length 3 है, इसके लिए length 5 है, but both are odd length paths. But that property valid is discarded here. X can be reached either through odd length path. In that case, you couldn't find an augmenting path, or you can reach through an even length path, where you may get an augmenting path. Okay, so x can be reached. So any vertex on the odd cycle, can be reached from an unsaturated vertex through some alternating path of opposite parity. Okay, so that is why one may miss the augmenting path if we go by a shorter path. So UVAX y, in that case you couldn't find an augmenting path, whereas actually it exists. So based on this observation, Edmonds has defined something. So these are the things which are basically some definitions he used to describe the algorithm, but I don't read it like this. Okay, I will read first. Let M be a matching in a graph G and let U be any M unsaturated vertex. That means like matching a graph ke andar, and U is any unsaturated vertex on that graph after this matching M. Now, he defined three terms: flower, stem, and blossom. So, what is flower? Flower is this part: U, V, A, B, C, D, X. ये part Y and Y vertex and this H को छोड़ के बाकी जो चीज है that is the flower. Okay. Stem is this even length U to A. This path is called stem, and A, X, D, C, B, A. This is called a flower. Okay. So flower is nothing but an odd cycle. Blossom. So flower is the whole thing. Flower is the whole thing. This odd cycle is called a blossom, and this stick, which starts from a stick of even length, is called a stem. So if we go by the definition, a flower is the union of two M alternating paths from U, which is an unsaturated vertex, that reach a vertex X on steps of opposite parity. So U is any unsaturated vertex after this matching. Then if you reach any vertex X through two different alternating paths of opposite parity, then that is called a flower. The whole thing was called a flower. Their union called a flower. The union of those two paths called a flower. The stem of the flower is the maximal common initial path of non-negative even length. So this is called non-negative even length, right? So UVA is the length at 2. This is called stem. Now it cannot be odd length. Why? The reason is I always start from an odd vertex. I always start from an unsaturated vertex. So it comes out with, so the way we find alternating paths is first we go by unsaturated edge, followed by a saturated edge, and from there, if I want to get a flower, there must be two unsaturated edge out of it. If there is any unsaturated edge here, only single unsaturated edge, then it must be a augmenting path. If there is an unsaturated edge here, it must be an augmenting path. Okay, so basically, the stem of the flower is a maximal common initial path of non-negative even length. Okay, the blossom of the flower is nothing but the odd cycle obtaining by deleting the stem from the flower. Okay, in example, the flower is the full graph except Y. The stem is UVA and the blossom is this 5 cycle. So UVA is the stem, this is the odd cycle, which is called a blossom, and the whole part except this Y part is basically the flower. Now, to develop the algorithm, there are two basic observations. So what is the problem? The basic problem, the first thing is, you first admit that it is an unweighted non-bipartite graph. If you start from an unsaturated vertex, it may so happen you can reach a vertex X through an odd length path as well as through an even length path, which basically give rise to the flower. Okay, now the observation is these blossoms means this odd cycles. These odd cycles do not hinder or impede our search. From each vertex X in the blossom, some M alternating UX path reaches X from the stem on a saturated edge. So the first observation is, it says that suppose you start from an unsaturated vertex, you take any vertex on the blossom except the vertex through which you enter into the blossom. Okay, but it says suppose you start a search from an unsaturated vertex and you go by unsaturated edge followed by a saturated edge and you go into the flower. You go into the blossom. That is the odd cycle. Then every vertex on the odd cycle except the one through which you entered so basically every vertex on this odd cycle can be reached through a saturated edge. जैसे इस vertex को इस saturated edge से you reach कर सकते हो, इस vertex को इस saturated edge से reach कर सकते हो, इस vertex को भी इस saturated edge से तुम reach कर सकते हो. Then like x को भी तुम एक saturated edge से reach कर सकते हो, u v a b c d x. Okay, so that is the first observation. Blossoms do not impede our search. For each vertex X in a blossom, some M alternating UX path reaches X from the stem on a saturated edge. The second observation is, since each vertex of a blossom is saturated by an edge on this path, no saturated edge emerges from the blossom except the stem. So, a second observation is the main observation. The first observation was that every vertex in the odd cycle has a saturated edge associated with it. First observation. Second observation says that even if suppose some matching is there, these red colored edges are basically the matching. If some edges are coming out of this blossom, that edges must be unsaturated edges. Why? Because all these vertices are saturated. So except this vertex through which we enter into the odd cycle, except this edge, except this stem, for all other vertices, that is for B, X, C, D, if there are any edges coming out of it, it must be a blue color edge or it is an unsaturated edge. So since each vertex of a blossom except the vertex through which I enter into the stem, so each vertex in the blossom is saturated by an edge on this path. So no saturated edge emerges from the blossom. So ये दो observations के basis में ये algorithm में एक चीज है that is called contraction of the blossom. So we will discuss it with an example. Okay. So ये चीज मैं रीड आउट नहीं कर रहा हूं. मैं what I will do, I will explain the whole algorithm through a. So ये जो चीजें मैं लिखा हूं, it's for you. You read it. Okay. I start from here. With this graph, this is an non-bipartite graph. Is a general graph, and our objective is to find matching. Now, Bart's theorem says that you find the augmenting path. If you find an augmenting path, then you revert the status. Then you revert the status of the edges. Okay, let's see. Say for example, in this graph, initially all vertices are unsaturated. Suppose I start from A, that is an unsaturated vertex. I see that from here I start an alternating path which start from an unsaturated edge and I reach an unsaturated vertex. So since AC both are unsaturated, I get an augmenting path. So I make it red. Okay, so this is the matching. Then I find another vertex which is unsaturated. Suppose that is B. So BD is another matching edge. Then FE is another matching edge. Then GH is another matching edge. Okay. Now I see that now U is another unsaturated vertex. So what I do? Okay. So I make two partite. One is called S, another is called T. Okay. So initially S contains U, the unsaturated vertex. The partite T is null. T is a set which doesn't contain any vertex, and every vertex in the graph is unmarked initially. It is unmarked. So unmarked is doesn't sense. So some flag is being used. Suppose flag is 0 for all the vertices. We say the every vertex is unmarked. Now what I will do? I will check all neighbors of U. So only those neighbors of U which are not in T. So U का एक neighbor है A, दूसरा neighbor है B, and none of them are in the partite T. So what I will do? I start a BFS from U, explores neighbor of U which is not in T, which are not in T. Okay. Now from U, I start a BFS. I reach A. A is saturated by an so I am going for an M alternating path. I start from an unsaturated edge followed by a saturated edge. So S contains all those S contains U along with all the vertex that can be reached through some saturated edge in the M alternating path. So S is the set of vertices that can be reached through some saturated edge in an M alternating path. T is the set of vertices that can be reached through an unsaturated edge in an alternating path. Okay. So saturated edge से जब जिसको हम reach कर सकते हैं that is S. Unsaturated edge में जो reach कर सकते unsaturated edge में जो हम reach कर सकते हैं that is in T. So U से मैं start किया algorithm. I reach A, C. So C is I reach C through a saturated edge. So C goes to S and A goes to T. I explore the edge AC. Then since it is a BFS, I go to U to B, B to D. So I reach D through some saturated edge. So D is appended to S and B is appended to T. Now so all the neighbors of U are explored. So we mark U. Then I explore the neighbors of C. Okay. Which is not in T. So C का दो neighbor है F and E. None of them are in T. So first I go for F E edge. Okay. C to F, F to E. So I reach E through a saturated edge Fe. So E will be in S and F will be in T. Now it may be the other way around. So here I assume that C, F, E in this order the search is happening. If it is happening in the other way around, like C, E, F, in that case what happened? That I reach F through a saturated edge. So F will be in S and E will be in T. Okay, that's why I write edge FE, not EF, for your understanding. That means my search direction is from F towards E. That is why I reach E through a saturated edge. So E will in S and F will be in T. Now C के जो neighbors, now C का first neighbor था F, C का दूसरा neighbor है E, but when it goes to E, it sees that E is already in S. E is already in S. इसका मतलब है कि I found an odd cycle. So vertex E belongs to S, is a neighbor of C. It means that an odd cycle is discovered, a blossom is discovered. So we mark C because all its neighbors are covered. So mark C, and we say that blossom has been discovered that consists of C, F, E, these three vertices. So what Edmonds do? He will replace these three vertex by a super vertex which is called capital C. Is replaced by a super vertex capital C. So in the next page you see that these three vertex will be vanished. Instead of it there is a big vertex out here which is called a super vertex. Okay, so this is that vertex. Again you look it. So D, this C, and so if the whole thing got merged, then D is adjacent to a super vertex C and the super vertex C is adjacent to G. D is adjacent to C and C is adjacent to D. This is a capital C, it is not the earlier small c. So basically you consider there is a very small triangle out here. Okay. Now what happened? So blossom has been discovered which consists of CFE and is replaced by a super vertex C. At the same time, what we will do, when the super vertex is discovered which consists of C, F and E, we update the set S and T. So we remove C, E, F, we remove C and E from S and F from T, and this super vertex is introduced here. So यहाँ पे क्या होगा? Earlier C and E will be removed and capital C will be inserted. So it will be U, D and capital C. Capital C stands for the super vertex, and from here F is removed. So basically what I am trying to say is, from C when I go to E, it is in S. So I found that it is an odd cycle. So odd cycle में जितने भी vertex हैं, they should be removed from S and T. So C, E and F will be removed. So it is U, small t and AB. Along with that, this three vertex is replaced by super vertex capital C that should be introduced into S. QT is there, capital C is introduced here. Now you start search from D. So explore neighbors of D which is not in T. So D के neighbor कौन कौन है? एक है B, एक है C. But B is already in T. Since B is already in T, we should not explore this. We should not explore this. From D we reach C. From D we reach C. Now C belongs to S. So again a blossom found. Vertex B belongs to T. Vertex B is not considered in this search because it belongs to T. But vertex C when ऐसा, so D के दो नहीं पड़े, एक है B, एक है C. B को मैं consider नहीं करूंगा. I won't consider B because it is already in T. D का neighbor जो C है, I will consider it, but when I going to consider it, I see that it is already there in S. That means there is a odd cycle detected. So I mark D, and the odd cycle detected that consists of D, B, U, A, the normal vertex along with the super vertex capital C. And all these vertex should be replaced by a super vertex capital U. Okay. So what is U? U is nothing but, so U represent, the super vertex represent this odd cycle which consists of small u, small a, small b, small d and capital C. Okay. So this whole thing will be replaced by capital U. So there is so this kind of thing will appear. Now what will be the status of S and T? So यहाँ पे UABDC, everything goes to this cycle. So everybody will be deleted from this. So S is null, T is null, and the super vertex U will be inserted into S. Okay. So super vertex U is inserted into S. Now I start a search from U. Okay. And I will search all these vertices, all its neighbor which are not in T. Okay. So suppose explore neighbors of U which is not in T. So U का एक neighbor है G which is not in T, and it is saturated by an GH. So H is reached from U through a saturated H. So H will be added to S and G will be added to T. U का एक दूसरा neighbor है X. Vertex X is a neighbor of U which is unsaturated. That means we found an augmenting path UX. We found an augmenting path UX. So basically हम लोग जो सर्चिंग चालू हुआ था मेरा स्मॉल यू से चालू हुआ था, and I through some conversion I reached to another unsaturated vertex X. So I get an augmenting path. Since I get an augmenting path, I need to expand the blossom. Okay. So what I do, when I reach X from U, I find it is an augmenting path because it's unsaturated. Now I need to expand U. If I expand U, what will happen? This will come. Now X to B I go. Okay. I know that B is, so now so it is an unsaturated edge. So I need to find, so there are two options, BU and BD. So in which direction I should go? Since it is an alternating path and it is an unsaturated edge, I will go by a saturated edge. So XB is there. I must go by BD because it is an alternating path. XB, BD. Then from D, we have only one option. I reach C, but I see that when I reach C, it is a super vertex. So I expand it. Once I expand it, I get this. So D2, जब मैं इसको, तो basically D2 यहाँ पे मैं जब या तो DC को मैं expand किया, so I reach E. Now there are two things. There is an unsaturated edge, there is a saturated edge. So since D is an unsaturated one, I must by saturated one. Since it is alternating path, I go by EF. Okay. From EF, I go by FC. This is an unsaturated edge. Then CA is a saturated edge, and AU is an unsaturated. So I found an augmenting path: XB, DE, FC, AU. Okay. And when I reach U, I find that it is unsaturated. So I stop here, and I get an augmenting path, UX augmenting path. So what I will do, I will revert the status of the edges. So XB become red, BD become blue, DE become red, EF become blue, CF become red, AC become blue, UA become red. Okay. So I get a matching. At this stage, all the vertices are saturated. So I find the matching. I find the maximum matching. So no more augmenting path can be found here. So that is how this algorithm works. Now, just a minute. Now this algorithm, to implement this algorithm is not that easy. Okay. So we will try to discuss some implementation details, which is not there in the book. So up to this, these things are there in the book, but these implementation things are not there in the book. So what happened there? So initially we have this matching. Okay, you for the timing you ignore this arrow. You don't think there is any arrow here. So initially A, B, C, D, E, F, G, H like this, and A, C, B, D, F, E, and G, H are the matching edges. Now what happened? You find any any unsaturated vertex U here. You see all its vertices, all its neighbors which are not in T. Okay, you see that A, B both are not in T, so you go to A to C. There is a saturated edge. So since you start from U, there is an arrow here, and AC is a matching edge. So you know that when you come back to C, you have to go to C to A. There is no other option. But from A, there may be multiple edges, multiple blue edges coming out of it. So since you start from U, you have to, in your data structure, you have to maintain from where you reach A. From which unsaturated edge, through which unsaturated edge you come to A. So you start your search from U, you reach U to A. So A ka previous hai U, that thing you have to maintain. Then you have to go by AC. There is no other choice since it is a matching edge. Then here you have two options. Here in this discussion, we go by CF, FE. So since you go by CF, F ka parent hai C, and this is a matching edge. Okay. Similarly, यहाँ पे भी U to B, you have gone. So B का parent है U, and you have to go by BD. Okay. So now when from C, when you do a BFS, first you reach UFE. Then when you reach from C to E, you find that E is already there in S. If you go here, so what happened? Initially U is in S, T is null, and every vertex is unmarked. Now explore neighbors of U. A and B are neighbors of U which are not in T. So you do a BFS. So initially first मैं C को include करूँगा because C is reached through some saturated edge, and A को मैं T में include करूँगा. Similarly यहाँ पे D को include करूँगा since it is reachable from U through some saturated edge, and B को मैं T में include करूँगा. And I mark U. Okay. Then एक्सप्लोर नेबर्स ऑफ सी. सी के जो नेबर्स हैं इसको मैं एक्सप्लोर करूंगा. सो सी का नेबर है एफ एंड ई. सो जब मैं यहाँ पे यू सी डी ये सब मेंटेन कर रहा हूँ, यहाँ पे एक एरो आ गया. ए टू यू देयर इज एन एरो, बी टू यू देयर इज एन एरो. सिमिलरली एक्सप्लोर नेबर्स ऑफ सी which is not in T. If none of them are in T, so first suppose I considered U, edge FE. So E will be there in S, F will be there in T. Next, I explore the neighbor of C, which is E, but E is already there in S. So I found it. So when I include this E and F, there is an arrow here. So there are three arrows. A to U there is an arrow, B to U there is an arrow, F to C there is an arrow. But C to E when I reach, I see that E is already belonging to S. So there is a what I should say. So there is an odd cycle. Now when I get an odd cycle here, I say that CFE, this triangle, this odd cycle is replaced by a super vertex capital C. Why capital C? The reason is I come through CFE and I come from C to E. So this is even length path, CFE, this is an even length path, C is an odd length path. Then how do I find this? So it is an odd cycle. So what I do, I will try to reach the lowest common ancestor of this path. So when I reach vertex E belongs to is a neighbor of C. So I know there is a, at this point I know that there is a odd cycle. Now from E, I trace back to C. Also from E, I trace back through E to F, F to C. And I found this is a lowest common ancestor. So here is the starting of the cycle. That is why capital C is basically my super vertex. Okay. So how you implement this lowest common ancestor, that is a challenge. That is not that easy. I have that code with me, but that is not very easy. So the data structure is quite involved. There are multiple data structures you need to maintain to find out this odd cycle. Now you replace this with a super vertex. Now in actual implementation, you do not remove this C, F and E and you replace it by C. That is for pictorial part. What we actually do, we do this thing. C comma capital C, F comma capital C, E comma capital C. That means all of these vertex belong to the set capital C. Okay, and this arrow now, I think it is clear to you. Now from this set, so yeah, so blossom has been found that consists of C, F and E by lowest common ancestor C of paths along EC and EF. EF path means E to F and replaced it by a super vertex capital C. So there is no replacement here. Basically each vertex का एक status में रखूंगा capital C बोल के. It says that this belong to a super vertex capital C. Now again so when this becomes a super vertex, when this becomes a super vertex, from here I start my search. Now D is already in T. It's so E के दो neighbors है, मतलब ये super vertex capital C का दो neighbors है. एक neighbor है D, एक neighbor है G. Now sorry, ये super vertex का एक neighbor है D and this D is already in T. This D is already in the set T. That is why यहाँ से search कोई continue नहीं होगा. But ये super vertex का, but this super vertex D का और एक neighbor है. So D का दो neighbor है. एक neighbor है B, which is in T. D का एक neighbor है ये super vertex itself. So it says that this triangle is also belong to an odd cycle. So अगर ये लेन देखो 1 2 3 4 5 6 7, so this is also an odd cycle. So that is being replaced by U. So every C is now converted to U. And why U? Because here you find out that there is a odd cycle. So you go by here and you go by, so basically from here you start a search. One is BU, another is B to D, D to E, E to U, U to C. Sorry. So suppose at this stage the question is how do you find that U will be my super vertex? Suppose from B, so B का parent कौन था? U था. Suppose you reach here, B का जो दूसरा एज होगा that must be saturated edge. So you go by BD. D का parent था E, so you go to DE. E is matched to F, so you go by this. F का parent था C, so there is an edge. CA is a matched edge, so it is a matched edge. Then A का parent था U, so U is the lowest common ancestor. That is why the whole thing is replaced by U. So this replacement is actually done by a separate field is kept where capital U is being maintained. Now from here you explore. So this whole thing is a super vertex. From here you explore. This is X and X is a unsaturated vertex. So you discover a that is replaced by U. Okay. Now, so the same thing is being repeated actually. We don't need to write this. Now, X is an unsaturated vertex, and I know that now it is an augmenting path. So, unsaturated vertex X has been found from B, thereby discovering an augmenting path. Now, what I do, I will find a new matching by inverting the edges. So, X to B I go, then I have an only option to go by these red edges. D का parent था E. ये parent जो मैं बता रहा हूँ बार बार, that is through the that is decided by your BFS. That is decided by your breadth first search. Okay, this parent is with respect to the breadth first search. Okay, so D के parent है E. E is matched to F, so you go by EF. F to, so you find that augmenting path X to B, B to D, D E, E F, F C, C A U. Now you change the status of the edges, and you find this new match. That is how this algorithm will work. So what you do, so today I will share you both the slide, this slide along with the matching slide. You read this algorithm once and try it with different kind of graphs. Okay, having few odd cycles within that. Then you can understand that why this algorithm is working. It's not that difficult. So first what you do, just you read this part. What is S, what is T? इसका meaning यहाँ पे लिखा गया है. So this is the algorithm that is being written here. Advanced Blossom algorithm. Okay, so I don't read it because there is no point in reading it out here. So it says that from an unsaturated vertex, how can I define S and T, and how can I say that is I get an augmenting path. When I say there is an augmenting path, when I am saying that it is a blossom, if the blossom is found, how it is being contracted, how it is being contracted is not mentioned in the book. The book says that if I find a blossom, I will contract it. And if I get an augmenting path, I will trace back the path. And when I get a super vertex, I will expand it. But how you expand, how you contract, those things, whether you use BFS or DFS, nothing is mentioned. Okay. So, so today I will send you 3 different things. The first thing is the normal matching slide that I have told you, that I have discussed with you. Second thing is this slide, and third thing is the original paper by Edmonds. It was discovered in 1965. So these 3 things I will share with you today. Okay. So with this I end today's class, and thank you.
Thank you.